I am Deepesh Yadav. I come from IT Bombay. I'm a PhD student there. So this is the microstructure. You are looking at many defects. You will see this microstructure many times in the coming slides. So let's talk about the content of my presentation. First, I would like to talk about the background and the gaps in the literature and the motivation why we are doing it. And then we talk about the methodology, how we did the mechanical test and all, and then we results and discussion, and then a little bit about conclusions. So first actually, this is the microstructure that I showed in the first slide. It has this is the cross section of thermal spray coating. This is the nickel coating, and you can see these are porosities and and these boundaries, and these are the defects basically. And if someone is thinking about the defects, they will reduce the mechanical property, fracture properties, and all. So we think in terms of that only when we think about the defect. So that's what's happened here. We done the uniaxial tension test on the freestanding coating, and this is the nickel coating, which has ductility, but when you see there is a very less amount of strain here, and the failure is taking place like a brittle ceramic. It's a nickel coating, right? So it can be seen by the flat surfaces also. It's behaving like a brittle material, and the failure is taking place suddenly. So that's what we want to. So that's what the defects are doing here. So they are reducing the mechanical properties. And when we see the fructograph, it was clear that the failure may be initiating at the defects. So what we went through, we start looking for the literature. Okay, how can we use those defects to improve the fracture resistance or can eliminate this sudden failure? Sudden failure is the cost of lives and the human lives and the structure and the money also. So so first, the first AJ Cook actually they create the interface in the Pmma and they eliminate the catastrophic failure by deflecting the crack. So that's what they created the interface. And the other one, Clark actually create the laminated structure of the silicon carbide and found out the increase and eliminate the catastrophic failure. So like this, actually, when you increase the number of porosity in the interlaminary structure, there is an increment in the fracture toughness will also take place. And while using the second phase material, you can, by the ductile phase material, you can blunt the crack at increasing the specific energy, the fracture energy. So that's what people are doing. So we, like the hole, you can create the hole and increase the fracture toughness. And like while creating even the extra plane of the porosity will help you to increase the fracture toughness by the 22%. So so while using those things, we make the conclusion key, okay, these are the thermal spray coating and we have these defects. So what we actually did, we inspire from these porosities and we took these, hole and splat kind of porosity. Hole is inspired from these kind of globular porosity and the splat is inspired from these inter-splat boundaries. So what they are doing with the structure that we are going to see, and we artificially created those structure. And first we have to do the fundamental study because none of the literature has done that. We want to understand how the hole is going to affect when it's interact with the crack and how the splat is going to affect when you interact with the crack. So first we quantify the integral in terms of the size of the hole and splat. And then we decide a unit cell. Then we give that unit cell by using those unit cell. We'll give the full scale architecture and quantify the fracture resistance. So here in this case, we can only check with one size of the architecture. The interaction can't be seen it here because when you increase the size, there is a reduction in the ligament length. So the load bearing capacity has been gone down. So before the crack propagation, the failure can happen between the ligament length. So in order to do that, we increase the size of the sample to see the effect of size of the feature to just understand the interaction between the features. So that's the methodology. Then coming to the mechanical test, we have so we create the architecture in two ways. These architecture in two ways by the laser cutting or by the additive manufacturing, because these are the very conventional process and easy to use. So that's what we use the So these are the 3D printing itself has some inbuilt architecture. So we need to quantify, we need to quantify those also and quantify the mechanical properties in order to use in the simulations methodology. So we did all of the tests on the SENV, single edge notch bending, and that's how and measure the CMOD while using the DIC camera here. And we recorded the images during the test, and we processed them with the big 2D software and determine the strand mapping and the CMOD. And we quantify the fracture resistance in terms of the work of fracture, and the work of fracture, the initiation work of fracture defined as well. The crack is initiate from the notch, and the increase in the crack length. This is the energy. This is the this is the area under. This is the area under the P CMOD curve and load and CMOD curve. Basically, integration of that, and that is the increase in the crack. That is increase in the crack length, increasing the crack area basically, and the total work of fracture is defined while using the total under area of the curve and increasing in the crack like in that in the whole test procedure. So yeah, so we define the dissipation energy also, because some of the energy is also consuming creating the plastic zone size. So we reported that also. Yeah, so as I said, we also optimize the size while increasing the diameter of the hole and is flat. And in this case, you can see the crack driving force of the J integral, the normalized J integral is increasing with increasing the size of the hole. This is because of increasing the compliance phase material in front of the crack tip that will lead to increase in the crack driving force. So that will, that will give you the indication, okay, if I increase the size of the hole, that means the crack driving force is increasing, the fracture toughness may be reduced. So this is the idea behind it. So when we tested it, but we found actually there is a reduction in the stiffness also when the crack is interacting with the hole. And when you see it here, you can see when you're increasing the size, the crack is interacting with the hole. There is a reduction in the stiffness. This is the when the crack is just initiating from the notch, and this is the load at which the crack is initiating from the hole. So yeah, so this is the thing, the load bearing capacity is increasing, and also the stiffness is also decreasing with increasing the size of the hole. Surprisingly, when you see the stress at the notch tip, stress at the at the hole type, it's reducing when you increasing the size of the hole. And interestingly, when you see the fracture toughness, this is the initiation fracture toughness when the crack is initiating from the notch, and this is the fracture toughness when the crack is interacting with the hole. So there is an increment in the fracture toughness. So there is a counter-initiative results with the crack driving force. Crack driving force is increasing, and the fracture toughness is also increasing. So this is the conclusion from there that, this is because of the blunting of the crack. When the crack is interacting with the hole, then the radius of the hole is also increasing. That will lead to blunting effect on the blunting effect, and that will lead to increasing the fracture toughness like 2 times of the initiation fracture toughness. So they might be useful to increasing the fracture resistance. Yeah, so the stiffness decrement can be seen here when the crack is interacting with the hole. And yeah, so as I said, we also optimize the distance between those 2 features while keeping them apart. You can see it here, the J driving force when the sorry, when the crack driving force is decreasing with increasing the spacing between them. So that's what's, it's reaching the bulk value because there is no more effect when you increasing the spacing between them. And yeah, so in the case of split, you are not getting any statistical result because of the stress around the features and around the crack tip is affected by the interaction. So that's why you are getting the zigzag, the zigzag variation of in the crack driving force. So split is more complicated, and here is the experimental results with the architecture, with the full-fledged architecture. You can see in the case of bulk, the crack, once the crack is initiating from the notch, there is a catastrophic failure. And in the case of whole architecture, when you have only the hole, the load bearing capacity is not going down. It's increasing when the crack is interacting with the hole. And that's what That's what can be seen any and every architecture, and you can see there is no sudden failure here. And in the case of a hole, the crack is blunted by the hole, and in the case of splat, is deflecting at the 90-degree angle. And when you have the in the SR case also, you can see it's interacting with the splat at the center of the splat, but it's initiating at the corner of the splat. So here the crack propagation is going from mode 1 to pure mode 2. And so then we see the effect of the blunting plus the deflection. You can see there the crack is blunted by the hole and deflected by the splat. That was leads to increase in the fracture resistance, so that we quantify the fracture resistance, the work of fracture, which is coming maximum in the case of SR. You can see the bulk. The bulk is very tiny, and you can see with the architecture case, it's very high. It's around 7 times increment can be seen. Yeah, so this is the they are eliminating catastrophic failure and also increasing the fracture resistance. And when we see the size effect, like we increasing the sample size also, there is a sample size effect can't be seen, but when you increase the diameter of the hole, there is a slight increasing in that. But when you increase the number of layer, you can see here the 3 number of layer and here the 6 number of layers. That increment in the number of layers is more effective in increasing the crack driving force. Now talking about inbuilt architecture in the 3D printing that you can see, there is at 90-degree when you have when you have the raster 90-degree, there is a deflection in the crack that will lead to increase in the load bearing capacity compared to the 0 and 45-degree. But when you have the orientation in a different direction, there is a crack will interact at the interface, and there is a crack is propagate in the catastrophic manner. So that's why the load bearing capacity in the 45-degree coming least compared to the 0 and 90. But here the 90-degree case even is coming maximum. So we give this architecture in the Pmma, and we print those architecture with the help of fusion deposition modeling. You can see there is a catastrophic failure in the case of bulk, but the load bearing capacity is also highest in the case of bulk. But when you have in the bulk case, the crack is not going straight because of the plasticity in the PLA structure. The PLA has a little bit plasticity. So when we see the 3D X-ray tomography, you can see there is a failure is starting. It's not interacting with the hole. It's a failure. It's interacting with the boundary of the hole. So this is the effect of 3D printing. So when we quantify the work of fracture or the fracture resistance, this is coming SH case with the maximum because of the blunting and the crack deflection. And we saw the rising R curve for each and every architecture, and the simulations results is also matching with the experiment results. So here are some recommendations in the case of when you are giving the Morse code architecture about the key size and spacing between them. It is the linear elastic fracture mechanics of the Pmma, and this is about the PLA. That's all. These are the references. If you are interested, you can go through them. And thank you. Thank you very much.